Alrighty, we are going to be talking about continuity at a point. And we need three conditions for a function to be continuous at a point. The first one, f of c is defined at that point. The second one, the limit of x approaches c exists. In other words, we want to make sure that the left-handed limit and the right side limit exists. And then the third condition is just basically the second condition and the first condition combined, aka is f of c equal to the limit? And if it is, then we know that our function is continuous at that point. All right, so we're going to do a couple of examples. Here, we want to find values of a and b to make the function continuous using our lovely formal limit notation. All right, so here, what we're going to do is think, okay, if I have to make the function continuous, I have to make sure that the limits are the same. And if the limits are the same, this means that my left side limit and the right side limit needs to be the same. So I have the limit as x approaches 2 from the left of f of x. And this needs to be equal to the limit as x approaches 2 from the right of f of x. Now I know that this right here is, let's see, ax squared is equal to the limit as x approaches 2 from the right of 2x plus a. And now I am going to use, of course, substitution with my x. So using substitution, I'm going to plug in 2 here. 2 squared is going to give me 4, so I have 4a is equal to 4 plus a, and then I'm going to solve for a. So 3a is equal to 4. 4, let's see, that means that a is going to be equal to 4/3. Yay. Likewise, same thing here, except I have 3 subfunctions, which probably means I'm going to have to use my limit notation twice, one at 1 and then one another time at 2. So I have the limit as x approaches 1 from the right of f of x, and this needs to be equal to the limit as x approaches 1 from the right of f of x. So I have the limit as x approaches 1 from the left, which is x plus 1. This needs to be equal to ax plus b. Now this right here is going to give me 2 is equal to a plus b whenever I plug in x. And then I'm going to do the same thing for 2. So the limit as x approaches 2 from the left of f of x is equal to the limit as x approaches 2 from the right of f of x. Oh, beta. Let's see. That's going to give me ax plus b is equal to 3x. I'm going to substitute in 2, so I'm going to get 2a plus b is equal to 6. So now I have 2a plus b is equal to 6, and 2 is equal to a plus b. Interesting. A plus b is equal to 2, and then 2a plus b is equal to 6. I have 2 equations. I'm going to use a system, and I'm going to use elimination to figure out what my a and b values are. So I'm going to subtract, and that's going to give me a negative a is equal to negative 4, or is equal to 4. So if a is equal to 4, and then me substituting it in here, I'm going to get negative 2 for b. So I have a being 4 and b being negative 2 to make this function continuous at 1 and at 2. All right. So for number 3, we want to use the definition of continuity at a point to answer the following given the 3 functions that I have given you. So we are going to use the three-step process, aka f of c is defined, the limit exists, and then f of c is equal to the limit. If those three conditions are not met, then we are going to cry. So here, my first condition is f of x defined at 2. Well, we know that at 2, we have this right here. So I could say that f of 2 is defined. And I could say that f of 2 is equal to 1. Then I want to look at the limit. So I have the limit as x approaches 2 from the left of f of x. And this is equal to the limit as x approaches 2 from the left of 3x minus 5. And this right here is going to give me 1. I'm going to do the same thing here. The limit as x approaches 2 from the right of f of x. And that right there is cosine of pi x. And if I were to plug in 2, that's going to give me cosine of 2 pi. And cosine of 2 pi is 1. So now I have 1 and 1 right here, which tells me that the limit as x approaches 2 of f of x exists, and then you're going to explain why, aka because the limit as x approaches 2 from the left is the same thing as the limit as x approaches 2 from the right. And then, based off of 1 and 2, because f of 2 is equal to the limit as x approaches 2 of f of x, and because that's both equal to 1, this tells me that the function f of x is continuous at x is equal to 2. Perfect. Part B says, is the function h of x continuous at -1? Well, if I were to look at -1 right here, I want to see if it's defined at -1. If I were to look at this right here, -1 squared minus 1 is 0, and then ln of -1 squared, or ln of 1 is also 0. You might think, it's defined, right? Plot twist, it's not. And the reason why is because I don't have a defined function at -1 right here. Because this says x is less than -1, and this says x is greater than 1. So because of that, this tells me that h of x is not continuous at x is equal to -1 because h of x is not defined at -1. So we know that it's not continuous. Sad. Part C says, find the value of k such that the function g of x is continuous at x is equal to 3. So before I even look at g of x right here, I'm going to go ahead and write my little statement that the limit as x approaches -3 from the left of g of x needs to be equal to the limit as x approaches 3 from the right. 3 from the left is going to give me kx squared minus 2x. And then 3 from the right is going to give me 2x plus 3k. I'm going to plug in 3 now, so that's going to give me 9k minus 6 is equal to 6 plus 3k. I'm going to subtract the 3k, that's going to give me 6k is equal to 12, which means that k is equal to 2. So k is equal to 2 will give me g of x being continuous at x is equal to 3. Now these were easy peasy lemon squeezy because I gave you functions. Now what if I give you functions and graphs to answer these questions right here? We're doing the same thing where we're using the three-step process, but now we have graphs. So for 4a, we have, is j of x continuous at 1? Well, I gotta see if it's defined at 1. So here, j of x is defined at 1 when m of x is equal to 1. And here, that's true because that's going to give me 2. So I could say that j of x is defined at x is equal to -1 because j of 1 is equal to m of 1, which is equal to 2. Okay. Now I'm going to go ahead and look at my limit notation. So the limit as x approaches 1 from the left of j of x is equal to the same thing as the limit as x approaches 1 from the left of m of x. We saw that being 2. The limit as x approaches 1 from the right of j of x is equal to the limit as x approaches 1 from the right of 2e to the x squared minus 1. Now, if I were to plug in 1 into that, 1 squared minus 1 is 0, e to the 0 is 1, 2 times 1 is 2, so this is going to give me 2. Which means that here, the limit as x approaches 1 of j of x exists since my left side limit and my right side limit are the same. Okay, so now what I'm going to do is say, okay, since this is 2, and since my function is defined at 2, this tells me that because j of 1 is equal to the limit as x approaches 1 of j of x, and that limit and that function value is 2, this tells me that my function, j of x, is continuous at x is equal to 1. Yay! All right, part B, is the function k of x continuous at x is equal to 2? So here, I know that I have a defined function at 2 because that's p of x. And that here, if I were to look at p of x, is 1. So now I could say k of x is defined at x is equal to 2 because k of 2 is the same thing as p of 2, and that is the same thing as 2. Right? Nope, sorry, 1. Okay. So then I could say that the limit as x approaches 2 from the left of k of x is going to be the same thing as the limit as x approaches 2 from the left of m of x. And that's going to give me, let's see, t from the left. So that's going to give me t right here. I can already tell that this is not going to be continuous because guess what? This is equal to 1 and this is equal to 2. So looking at my function value from 2 to the right, 2 to the right is p of x, and we saw that p of x is 1. So because my limits are not the same, because my limit is not the same, this tells me that the limit as x approaches 2 of k of x does not exist. And this is why k of x is discontinuous at 2. Same thing for part C. I think you guys can do this on your own. For part C though, L of x is continuous at 2. You just gotta prove it. So that's that. In the next video, we'll talk about IVT, the intermediate value theorem, and then we'll call it a day.